Hello everyone, my name is Prashant and today I'm going to talk about the important component from performance perspective called network. Um, it's the part 4 of the series of the Linux performance tuning from scratch, and today I spoke about like what are different components of the network, how the two applications interact with each other, what are different tools we can use to debug any network performance issue, and what are the different tuning parameters we can use to tune the performance of the existing network. It is one of the important component, and on the other hand I can say it's one of the difficult component because there are a lot of components which are involved which are outside our scope, like switches and routers. But the performance of these components will indirectly or directly affect the overall performance we are getting or we are achieving. So that's why sometimes it's difficult in debug. It's one of the important component, and the other component are like switches and router. So before we can dig into the different like a different tuning parameters as well as different components which are involved, let's first look at like how the application communication take place between two of the applications. For example, I have one application A. Like this is my application A, and it want to communicate with the application B. So how this entire communication process take place? Let's first look at this. So, means Linux Linux, like many of the Unix system, uses a concept of socket interface for TCP/IP networking. And means what socket does is socket provides an interface for the this user side application. So let's say this is my application A, and it want to communicate with the application B, or it want to send some other data. So how it does, like it this application creates or generates some kind of a data application. Then this application opens the socket and write the data through the socket interface. So means this is our socket buffer, and at this moment of time you can consider socket as a file like object, and data is put into the in the transmit buffer. So socket is basically deal with the transmission of data. After socket, it reaches to a TCP/IP layer, which mostly consists of your four layer like data, TCP, UDP, IP, and Ethernet layer. And whenever the data pass goes to these each and every layer, the appropriate operation take place. For example, like the passing of the header, the adding and modifying of the header, the adding of the checksum bit, routing operation, fragmentation. The important thing we need to note at this point of time that whenever the your packet or whenever your data goes when the socket buffer goes down to the each and every layer, the data is not itself copied between the layer because this will create an extra overhead. So what Linux does is just change the reference in the socket buffer and pass it to the next layer. So this is one of the important things which kernel does, and it prevents the overall overhead of copying the data to each and every layer. Once the data means after this TCP/IP stack, the data reach to your NIC or network interface card, and network interface card do, it sends out the data and raise an interrupt when the data is transmitted. So finally, your data leaves this network interface card and reaches to the other network interface card uh, that is on the receiving side. And the first thing which will be happen is the matching of the MAC address. Like if this package is destined to this network interface card or for this application. Once the network address matches, the network interface card on the other hand receives this frame and uses a DMA or a direct memory access to copy the frame into its receive buffer. So after that, what network card eventually do is to move the packet into a socket buffer and issues a hard interrupt to the CPU. So like as I discussed previously in the process management section, like if like what this interrupt do is do the process of something called context switching, and too much context switching is always dangerous for the from the performance perspective. So what the new API does or the network API does is like kernels handles this hard interrupt and schedule a soft interrupt to handle this packet, and this prevent a phenomenon of live log. So means more about it you can refer to my this process management video lecture in which I talks about this interrupt, little bit about interrupt, and more of a context switching, like how this context switching, what is this context switching, how this happen, and how you can check like which process is doing the voluntary context switch or the non-voluntary context switches. And then CPU process this packet and move it up to the layer until it arrives at the particular destination port. So let's say if both of the application, like on this side, if this is a application which is like a Apache host, so till the your data reaches to the Apache port, which is by default is set to 80. So this is how the whole TCP/IP communication take place. Okay, so here we refer to something called SK buffer or socket buffer. So let's dig deep into what exactly is socket buffer. So the buffer and a queue, which we refer over here in this section, consists of your core networking read and write buffer, which constitute of both your TCP as well as UDP. So it is both your for per socket TCP read and write buffer, your fragmentation buffer, or as we see that the NIC buffer, which is used by a network interface card, or on the other we can say it's a DMA buffer. So basically kernel, you don't need to worry about these parameters, and kernel automatically adjusts these buffer based on the current network utilization. So means if we don't need to adjust these parameters, do we need to study about it, or do we need to tune about it? So here's the catch over here. So let's say by default, whenever you install your system or whenever your system boot, kernel automatically adjusts this parameter and by default set out to a value of 128 KB. But it's primarily depend upon what exactly you are doing with the system or what application you are exactly running on the system. So let's say we have two servers, one is a PRD server and one is a DR server, in which a nightly backup happens, and it is moving a bunch of data from your PRD server to the DR server. So in that case, whatever the value of this 128 KB is not enough. So in those cases, we need to tune the values, or we need to increase the value of our socket buffer so that it can accept more connection. So the other question is like, which has been asked by many people, that so why kernel will set it out to such a low value. So the value of this socket buffer, which is either a send buffer or a receive buffer for both TCP and UDP, is extracted from your memory. So just to save memory, kernel will set out to a lower value, because if you set out to a higher value, the kernel will take that much amount of memory from your RAM, and uh, this will be shown, means whenever you are going to increase this value, this will be shown in your memory part when you are going to indicate with the help of top or other command, that like a high memory utilization. And setting it to a too high value will cause a issue like a buffer bloat, and which will definitely impact the application which are doing a small number of write, for example your SH and all those applications. So please make sure like whatever value you are setting is to be means you will do a lot of like a round of testing before setting out these kind of a value. So our next section, I will discuss about how we can set these values and how can we tune these values to get an optimum speed. So before that, these are some of the tunables which we need to tune. So these are like, let's get a brief demo. So like I mentioned, these values can be increased for system to handle more packets. So let's say I have a system. System. Okay. Okay. Just one second. So basically what we need to deal over here is to something called a bandwidth delay product. So before going to bandwidth delay product, let's discuss about these parameters, which are your core parameters, where R is for your receive buffer and W is for your send buffer. So this core networking is the maximum socket receive and send buffer, which is used for your both read and write. Similar way, this TCP underscore mem is the system-wide memory limit for your TCP and UDP respectively. Okay, so let's reconnect to this machine again. Start the session. Sorry about that. And let's look at this value. I core mem. So here, like I already mentioned, this is for send and this is for receive buffer. So what this core value is, this is core networking maximum socket receive and send. Then you have something called for something values for TCP and some values for UDP, which is similar like a system-wide memory limit for both your TCP and UDP respectively. Okay, this for TCP and this for UDP system-wide limit, and this for TCP receive, this for TCP send. Okay, just make a note that these values are in pages. So if you need to know what is the default page size, then come out to the help of this much, which is 4096 or 4 KB. And this is the minimum value, this is the pressure, and this is the max. So whenever this is means kernel will generally, when this value reaches to about the min value, or when it touches to the minimum value, kernel is generally not interested in TCP UDP memory usage. But whenever this value touches to your pressure value, kernel start acting moderately till the value drop to the minimum value, and maximum is the maximum amount of TCP memory which can be used in the system for socket buffer. So, and remember one thing, the value of this TCP send and receive buffer cannot be exceed beyond your core networking values. So if you're going to increase this value, you need to increase the core networking value too. Okay. So bandwidth delay product, that is been the multiplication of your bandwidth as well as delay, which is the round trip time. So to calculate the buffer size, that is the maximum amount of like our main concern here is the throughput, that is the maximum amount of our data which can be transferred. We need to determine the time needed for the packet to travel from your local system to the remote system, and that's a multiplication of both your bandwidth, current bandwidth, as well as the time it taken, that the round trip time is called your bandwidth delay product. So let's see, let's restart this machine. Okay. Okay, change the font size to 14, something like that, and disable this. No, this session actually. Okay, so this machine is 1.9. Let's bring down the second network interface card down. So now this machine has one IP 1.9, and this machine has, wow, 1.9, 1.9. Okay, so I need to connect to the other machine, which is 1.12. Sorry about that. Just one last thing. Okay, so first thing I need to do is send out 3 packets to 162.198.1.9. Okay, so in this way I can calculate this round trip time, which is the average. So here if you can see, it's 1.501 millisecond. That is the round trip time. That is the time it takes for a packet to send from this local machine and return from the remote machine. So we are taking the average of that. And let's see the bandwidth. So ETH2. So here it's 100 Mbps. So now calculate the bandwidth delay product with the multiplication of these two. So this is millisecond, and this is in 100 Mbps per second. So let's use the calculator, which is in millisecond multiplied by 1000 Mbps into 10 to the power 6 into 10 to the power minus 3. So that means more 1000 divided by 8 to get a byte. So this much amount of bytes, and 1024 to get in KB, that is the 183 KB. Okay, so now let's for the time being focus on bytes. 187625. So before going to tune any of the parameter, let's run some results so that we have some baseline. Okay, now let's remove this file. Okay, so from other machine, let's run this command wget to the other machine from where we calculate the round trip time into test. So let's see how much time it takes to download this particular file, and once we applied all those parameters, how much benefit we'll see after tuning those parameters. So before going to change any of the parameters, let me tell you frankly that this is my virtual machine where I'm using an emulated card, that's the emulated network card, and everything is been routed from the same physical single network interface card, which is hosted on my hypervisor side. So you might not see much of a difference, but in a case of physical machine, when you have a dedicated network card assigned to that machine, you will definitely see a difference. So without anything tuning applied, this is the result which I got, that the real user and on the system side. So let me note down this value. Okay. Now sysctl-a grep-i mem grep-i core. So like I said, this is the core networking value for send and receive buffer. And let's not worry about the UDP right now. Let's worry about the TCP. Okay, so TCP is send and receive. Okay, Rmem underscore max, that is for receive. This for send. TCP Rmem and TCP, and change this value to this value. Okay, and min, it should be fine. Let's put the pressure to be the half of this value, that is 9 2 9 2 16 1 2, somewhat around half of this value, half of 187265. Okay, now let's apply this setting in your sysctl.conf. So vim etc sysctl.conf. Okay, I'm already playing with the system, so you will see these values. Okay, I missed something. Let's come out of this file. Delete. Insert. Okay. To read this file, okay. This is something outside of this, but let me tell you one thing. For example, so this is the value. Sysctl has one advantage, like if you are adding some value, which is like means it does some kind of a checking. So let's say I misspelled it as swappiness, and I'm adding a value of, let's say, 10. So it will check that whatever the parameter you are applying is correct or not. So let's see. So it's a error that this is a unknown key. So it will do some kind of like authenticity of the data. So let's put the correct value, and now it's changed to, and you can see it by this command. So it's set to 10. Okay, now remove that data test, and once again run that command. Get from underline. Okay, let me confirm that. Okay, let's run the same test again and see if there is any difference. So you will see a minute difference or might get a value which is you are not means you got a like some kind of degradation, but in most of the cases which I have tested, like you will see like some of the performance gain while tuning this parameter, because this is a kind of a optimum value for your TCP. Means we have set up optimal value for TCP and UDP, not UDP, only for TCP. So from 34 the value decreased to 22 now after tuning those parameters. Okay, so these are some of the things you can do. Now let's go to the next topic, window scaling. Okay, so what window scaling feature will provide us? So let's say like whenever you're going to send out like a, I'm going to discuss later about the three-way handshake. So whenever a sender sends a packet, it send out a SYN flag, and for each SYN flag on the receiver side you will get a SYN awk. So sender will send out a next SYN flex package till when it get a SYN awk flag back from the sender side, on the receiver side. And once it got the SYN awk packet, it's going to send out the awk back, and this is how the data transfer take place. So instead of getting awk for each and every request, we are just going to slide the windows from this to this. So for all this SYN, it is going to get a one delayed awk, so that sender doesn't need to wait for each and every SYN for awk for each and every SYN packet. So this is a feature of called window scaling. So like we see in our previous example, if your BDP value of BDP reaches above this 64 kb, then this is really handful. So we calculate this value as BC scale equal to 8 and 1024. So we are getting a 183 kb, approximately 183 kb. So if your value of this, your bandwidth delay product, exceeding beyond this value of like 64 kb, then you can utilize the concept of bandwidth delay product, or called BDP. Okay, so let me tell you something more in depth about it with the help of this figure. So whenever this sender sends a packet, so this window size is offered from the receiving host to the sending host by the window size field in the TCP header. Using it and using this window size, host can send more packet effectively because the sending host doesn't need to wait for the acknowledgement of each sending packet. And generally this TCP window starts slowly, and with every successful acknowledgement from the other side of the connection, means from the other means this window generally starts small and it increases slowly with the every successful acknowledgement, and this is generally been useful in a case of a high-speed network. So let's see how much improvement we will see if we can increase the size of this window scaling. So let's go back to our demo machine. So here we see that it's 22 now. Now let's say if I can type scale. So by default set to 0. Ctl-w insert equal to 1. Let's enable this. -rf the test file, so that okay. And now let's run the same command again. So we might need to see some performance gains after enabling this window. Okay, so let's see. And so like the main aim I said is to increase the maximum transfer size. So from 64 kb it will increase. You can use a tool like ethtool, or might you did not see any improvement because this is all been routed from a single interface card. So here it comes out to be more than that. So this is might be expected, or you will see like without window scaling it is working fine. It is actually working better than this. So I would suggest you to test in your physical machine rather than the virtual machine in which I am testing right now. Okay, now let's look at the other concept called ethtool. So this is the first tool I'm going to demo you. So basically we need to understand two factors like throughput, which we already discussed, like the maximum amount of data which will be transferred, and the latency, like the response time. So whenever your application sending out the response or sending out data, whenever it is getting a response back from the application side. So whenever clients send out any query, when it is getting a response back. So the let's look at this tool. Okay, now you have the machine. So no, sorry, yeah. So ETH tool without any option, it will give you some of the important statistics like this network interface card support 10 Mbps, 100 Mbps, 1000 Mbps in full duplex mode, and 10 Mbps and 100 Mbps in half duplex mode. Auto negotiation is on. Speed, it's 100 Mbps. Duplex is full, and the leading character is yes. Okay. Okay. Auto negotiation is one of the feature used by your network interface card, where it is negotiate with the next hop to negotiate the highest speed. So for example, you have this network interface card which is like 100 Mbps, let's say it's 100 Mbps or 1000 Mbps, while the switch interface is 1 gig, so or 10 gig network gig. So it is basically been used to negotiate the difference in speed. So it is normally trusted, but there are cases where it doesn't work. So wherever you see this huge difference between two networks, for example, from this machine and between the switch, you will see a huge performance hit. So generally you can turn this off with the help of this command eth0 auto neg. Okay, so like I told you, this is my virtual machine, and in case of virtual machine, these settings generally doesn't work for virtual machine, as their network link speed will depend upon the physical network card in the hypervisor. So if you run this same command again, you will see that auto negotiation is still on for this machine. Okay, so somewhere you will see auto neg support auto negotiation or auto negotiation turn off. Okay, cool. So transceiver and auto negotiation, you will still see it on. So I just run the same test on one of my physical machine. So here, yeah. So I just run the same test on one of my physical machine where this is the case. Okay, and here also the auto negotiation is on. I run the same command with auto neg off, and you can see in case of physical machine it is turned off. So you can test it on your physical machine, not on your virtual machine. Okay, the other thing you can do with the same command line tool is, for example, if you want to negotiate the speed from speed 1000 to 100, okay, you want to make duplex from full to half, all these things you can do with the help of ETH tool. Okay, anyway, these changes are not persistent. If you want to make these changes persistent across reboot, go to your network interface file, Vim eth0, and you need to add an entry like this called eth tools tool underscore opts is equal to auto neg off, and in this way you can turn out the auto negotiation. Okay, there are more things you can do with the help of this. For example, you can offload some of the configuration if your network card support. So let's see this. So one of the thing you can do is to turn TSO on. So what TSO is, generally this card doesn't support it because it's an emulated card. So whenever the packet more than 1500 bytes, like for example, you can see the default MTU size is 1500 bytes. So if there any package which is more than 1500 bytes reaches to your network interface card, it's a kernel responsibility to break the packet into smaller packets or equivalent to 1500 bytes. So this is generally been you can offload this configuration from your kernel to your network interface card. Nowadays, the network card interface card is smart enough to deal with these kind of a situation. So you can do it with the help of turning out this feature on TSO equal to on. Now, like we discussed about the bandwidth and latency. So how can we measure a bandwidth or latency between two different machines? Okay, uh, for both TCP as well as UDP. And this for this purpose we have a tool this called qperf, which can even measure for TCP, UDP, even for RDMA and for InfiniBand also. So for doing this, you need to run it as a server on one of the machine. Let's say qperf without any argument, and on other machine you can do it with the help of qperf, the IP of that other machine 1.9, and let's say I need to measure TCP bandwidth as well as UDP bandwidth. Okay. Same way, if I need to measure TCP bandwidth as well as TCP latency, I can do it. For more info, you can play with this tool with the help of this help examples. Here you can see the other examples. Okay. Now bonding. Bonding is an important concept, uh, and the major question before using a bonding is like why we need bonding. So, like say, sometimes we need more bandwidth than a single network interface card can provide us. So let's say we are working on an organization where upgrading a network card is not an option for us, like from going from 1G to 10G is not an option for us. Even if we upgrade our network card from 1G to 10G, that we do means we cannot get like for example a load balancing between those two network card. So to address this kind of issue, we have a bonding, which is nothing but to means we can bond a multiple network interface card to a single logical card, and the the means the behavior of this bonding interface will depend upon the bonding mode we have selected. So like we have different bonding mode. For example, balance RR or zero, in which packets are sent in the round robin fashion leak between using all the network interface card on the bond. So like for example, you have a ETH0 and ETH1 card which you have used for a bonding purpose. So the packet first sent to your ETH0 and then it goes to the ETH1 card. So in this way you will get a fault tolerance as well as high. Means in this way you will get a fault tolerance. Then the second mode is called active backup or mode 1. In this means in this mode one of the card will act as an active interface while the other will act as a backup interface. So in the case one of the card got down or one of the NIC got down, the other card will take care of the proceedings, and this will provide the fault tolerance. The next mode is called 8023AD or 4. So in that mode, for example, you have a two network interface card, both running on a 100 Mbps speed. So you will got a combined aggregated speed of 200 Mbps. But just remember one thing: the individual connection are still limited to a speed of your single network interface card. And the most important thing about it that your switch need to support means to configure this kind of a bonding, your switch need to support this kind of a bonding. So for more information about bonding, you just need to install the kernel-doc package. With a share doc kernel-doc documentation networking, and there is a file called bonding.txt. So here you will get a bunch of information about the bonding. Okay. So let's look at the demo part in which I'm going to configure bonding in one of the machine. So okay. So let's say yes. So I think this is my machine. Let's run on the physical machine itself. So this is my two network interface card, ETH0 and ETH1, and I'm going to configure a mode 0 bonding, which is a round robin. Means the packet is been transferred between both of the machine in the round robin fashion, like this balance RR or mode 0. Okay, so to configure this, you need to load a module. So I created a file called bond.conf, which I'm going to load a module called a bonding module, bond module. Make sure you can create a file with any name, but it should be end with the this .conf extension, the kernel will read it or your modproc command would read it. Now inside your 0, change your boot protocol to static. Okay, give slave equal to yes. Okay, and master equal to bond 0. The same. Let's leave it. Same thing you need to do for ETH1 also. Okay, static slave equal to yes and master equal to bond 0. Okay, just to save time, I created this file called fcfj-bond 0 and I need to copy it inside the network scripts folder. Okay, and just restart the service. Okay, just don't worry about that error. And now if you can run this, you will see your bond interface running on 1.20 ETH0 and ETH1. And to check more about it, you can check proc net bonding bond 0. So yes, so here you can see that your bonding mode is round robin, MMI status means it's up, and the network are involved is ETH0 and ETH1 with the speed of this hardware address and all this information. One thing I forgot to tell you, and if you notice that in this configuration file, I put network manager services equal to off or no. So still now the network manager is not supported for bonding, and I am using CentOS 6.2. So please make sure that this service is off before configure your bonding. Stop. Okay. Now let's go further. Jumbo frame. So that whenever a packet is transferred from transferred across your network, packet consists of header and a payload. So like I show you, the default MTU size is 1500 bytes. Okay, the default MTU size is 1500 bytes. So here if you can see the MTU size is 1500 bytes. So when it is transferred across the network, it consists of a different types of payload. For example, typical TCP packet include a Ethernet header, your IP header, and a TCP header. So all these headers are included in your MTU. So out of 1500 bytes, the 52 bytes is for protocol header, is for these different protocol header, that is TCP, IP, and Ethernet header. So this is overall a 3.5% overhead in terms of the overall size of packet. In UDP it's 28 bytes, so it's 1.9. So to overcome this limitation, or to overcome this overhead, there is a concept of called jumbo frame. Instead of transferring the packet of 1500 byte size, they have increased the size of the packet to 9000 bytes. Okay, so the only problem while implementing jumbo frame, that each and every piece of a networking infrastructure support it. Okay, And to enable it, you don't need to do much. Okay, etc is config network hyphen script vim if th0, and you just need to specify the MTU equal to 1500. Oh, sorry, 9000. And obviously, all your network equipment you need to configure that jumbo frames and whatever it is. Okay. Now let's look at the important concept called three-way handshake and how it is happened. So like I mentioned earlier, before any data is sent between the client and the server, connection need to be established. And the process of connection establishment is called a TCP IP handshake, three-way handshake. So like during this process, your client send out a SYN packet for remote host to request the connection, and remote host receive this packet and send back a SYN ACK back, and then client send an ACK packet to its peer host to complete the connection establishment. And once this is done, your data transfer will take place. Okay. Similar stuff happen when the client is closing the connection. So client send a FIN packet to the server to start the connection to start the termination process. Okay, server sends the acknowledgement of the FIN back to the sender if the receiver or the server doesn't need to send any more data back to the client. Client send an acknowledgement packet to the server to complete the connection termination process. So if you want to capture this uh, three-way handshake, you can capture it with the help of a TCP dump. So you need to have this TCP dump installed in your system, a software called TCP dump, and you can capture it with the help of this -i th2. If you do not using a default interface, tmp I say wireshark.pcap, which is the default capturing format. Okay. Source host is equal to 192.168.1.20, the bonding mode which we have just configured, and destination port is equal to 8. So here we start the TCP IP dump capturing. Means start capturing the packet from which are coming from this IP address 1.20, and the destination port is port 80. So let's generate some of the traffic. Generate 92.168.12. Okay, on port 80. Let's run this get host 1.1. Okay. Let's terminate the connection. So I already captured the one TCP dump output, and I want to demonstrate it to you. TCP dump from the server. And to see the output of TCP dump, you can, let's control C, then packet capture. You can use TCP dump -r and tmp wireshark. Okay. So at the same time, you can view this output in a GUI screen with the help of a GUI tool called wireshark. So here, if you can see, the clients send a SYN packet. In its reply, the server send a SYNOC, and once the client receive the SYNOC, it send out the awk, and then the data transfer takes place between the two of the machine. Okay. And tcp dump -r command you can see you can use to read this pcap file. Okay. But because reading it via the GUI is much easier, then it's always preferred. That's why it's always preferred. Okay. So this is a little bit introduction about networking. What are the network tuning parameters which we can use to optimize the performance of our infrastructure? Some of the tools like qperf, tcp dump we can use. So thanks for watching this video. In case of any query and question, you can please write it to me at gmail.com. Thanks once again.